Welcome to Basics of Noise and its Measurement. Over last two lectures we have been discussing this discrete Fourier transform, and what we have learned till so far is A, how to discretize a function, or if we have a discrete set of points, how do we use these points to compute the amplitudes of specific Fourier components. What we will do in this lecture is continue this whole topic of DFT, and we will also figure out how to extract the specific values of frequencies which correspond to different values of xk. So, that is one important thing which we will discuss in this lecture, and then the other thing we will discuss is something which we know as padding, and I will explain that as we come to that relation. So, that is what we are going to do, calculating frequencies and padding. Okay. So, the aim of today's lecture is that once we have generated values of xk, we have already figured out how to compute specific amplitudes of frequencies associated with each xk. And the way we do it is we multiply that xk with 2, each xk with 2, and divide it by the total number of points, which is capital N, and that is the specific amplitude of corresponding to each xk. Now, each xk is also associated with a specific frequency. So, that is what we will learn how to figure it out. Before we discuss that, I wanted to talk about something called Nyquist limit. So, in plain English, so this gentleman Nyquist, in plain words, what he said is that if your sampling frequency is 100 hertz, then the maximum possible frequency which you can extract by doing this Fourier transform, DFT, discrete Fourier transform, will be 50 hertz. So, in mathematical sense, what it means is maximum possible frequency which can be extracted and that is equal to sampling frequency Fs divided by 2. Okay. So, what does that mean? Our sampling frequency was 8 hertz. So, the maximum possible frequency which we can extract out of it was 4 hertz. Maximum possible frequency was 4 hertz. So, that is one thing. And associated with this is also this thing, because in last class I had said that you only consider the first 12 points or first half points and ignore the other half points. And the reason for that is, so again in a very broad loose mathematical sense, is that this approach, it gives you solutions for a direct problem and also a conjugate problem or a complex conjugate problem. So, the first half represents the solution of the direct problem, and the second half represents the solution for a complex conjugate problem, and somehow the energy overall it gets divided over the entire thing. So, the when you plot xk, if you plot on the y axis you have the values of xk, on x axis you have different values of k, you get a symmetric figure and the energy gets distributed. So, that is why you have to multiply it by 2 and get the original amplitude back. So, that is there. So, this is an important thing, that the maximum possible limit which you can extract is Fs over 2. And now, let us see what this means. Okay. Now, I am going to introduce 4 different frequencies. So, first one is the normalized frequency. Okay. And what is normalized frequency? You can calculate it as k over n hertz. So, if k is 0, normalized frequency is 0. If k is 1 and capital N was in this case 24, then normalized frequency will be 1 over 24. Okay. So, this is, then there is normalized circular frequency, and that is 2 pi k over n. So, each xk is associated with a normalized frequency, which is k over n. Okay. And remember, this is not the actual frequency, this is normalized frequency. And if you want to do it in angular velocity terms or circular frequency terms, you multiply it by 2. So, this will be hertz, this will be radians per second. Okay. Actually, I will not call it hertz, but it is because the units are unit, I mean this is a unitless entity. So, I will not call it hertz or radians per second. Then there is the actual frequency. Frequency which corresponds to xk, and that is k over n times fs, which is sampling frequency. So, this is actually, its units are in hertz or 1 over t units. And then there is circular frequency, and this is also actual, and this is 2 pi k over n fs. Okay. So, this will be what? Radians per second. So, you have different values of xk, and for each value of xk there is an indice which is k. The moment you know that k, you can calculate normalized frequency, normalized circular frequency, frequency and circular frequency. You know the value of, you know the amplitude of that frequency, and you also know the value of that frequency using this relationship. Okay. Now, let us look at this further. So, k was 0, 1, 2, 3, 4, 11, 12, and it went till 23. Okay. So, if you compute the value of frequency, that was k over capital N times fs, right. So, this one was 0, and what is the value of n? N was 24, fs was 8. So, fs over n equals 0.333, right. So, this is 0.333 hertz, this is 0.666 hertz, this is 1, this is 1.333. You come to this, so what? So, you come 9 would corresponds to 3 hertz. When k is 9, then 9 would correspond to 3 hertz. 10 would correspond to 3.333 hertz. 11 would correspond to 3.666 hertz, and 12 would correspond to 4.00 hertz, right. And what does Shannon say? That I cannot have any answer in this range. This Nyquist criteria, it says that. So, I have, again because of this I have to ignore this. Okay. So, I take only first 12 points. So, now you get a little better feel as to why we are ignoring these things. So, I take only first 12 points and I get the answer here. So, I know using this how to calculate okay. So, what we have figured out is that how to calculate xk. Now, this xk can be complex. It can be complex, there is no reason, right? And I also know how to calculate frequency, and I also know how to, okay. So, this is xk by itself. If I multiply this by 2 and divide it by 24, I get the complex amplitude. I get the complex amplitude of that frequency. Okay, do you understand this? Yeah. So, I get the complex amplitude of that particular frequency. That particular frequency will have a magnitude and a phase. So, the magnitude of fk, kth frequency, will be 2xk over n. The complex amplitude was 2xk over n. The absolute magnitude, because xk can be complex, so the absolute magnitude will be modulus of 2xk over n, and the phase of kth frequency will be tan inverse imaginary of xk divided by real of xk. Okay. Is this clear? So, we will recap. So, what do you do? If you have a set of data points, compute xk, right? Then compute complex amplitude of kth frequency, and this is what? Xk divided by n times 2. Compute Fk, and how do you compute Fk? It is k over n times Fs, right? And then compute, what do you do? Compute magnitude and phase of Fk using the relations which we have discussed earlier. So, this is the overall summary. So, if you know this, then you should not be having any problems in doing DFT or discrete Fourier transform of any signal. The signal can have complex numbers, it can have real numbers, it does not matter. You can do this. Last thing, and this what we are going to discuss is padding. Padding. So, suppose you have a signal in time and this is not a repeating signal, because we can use Fourier transforms for non-repeating signals. Now, I can discretize it here, 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 here. Let us say these are all equal intervals. This is the amplitude, right? Or let us say this is f of t. Okay. Now, what does this mean? Suppose this is t seconds. Suppose this is t seconds, right? So, then how many samples I have? 1, 2, 3, 4. My sampling frequency is how much? 4 samples in t seconds, right? Suppose this overall is t seconds, then it is 4 samples in t seconds, right? Then maximum possible frequency which I will get will be what? No. Maximum possible frequency information, it will not be 2, it will be Fs over 2, that is 2 over t, right? Suppose I want more points, suppose I want more information on frequency, suppose I want this number to be very high, then what do? I put more points. So, that is called padding. Okay. So, I can either interpolate between adjacent points, or if 2 points are close by and if I do not think it is going to change between 2 adjacent points, I just take a straight thing. So, that is called padding. So, I basically pad up all the information between 2 points. Then what happens? My frequency, this sampling frequency, it went up significantly. So, the maximum possible frequency components which I will get from this will be higher, will be much higher. So, this is called padding. So, this closes our discussion on discrete Fourier transform from the standpoint of having some introduction to it. In the next class, what we will do is we will have one more lecture on DFT, and we will learn a little bit more about it, and then we will close and move on to other topics. So, okay, thank you very much.